Definition 7.7. We again take two vector spaces over K and take a linear map from V to W. First of all, the so-called kernel of F, sometimes also called the null space of F. I think, for example, the book of Axler that I recommended writes null space, is the following. This is by definition denoted by ker of F. Ker F. This is the set of all vectors in V such that f of V is 0. So, in other words, the pre-image of the set which contains only 0. And so this is the notation here. Second construction, the image of F. This is basically, I have already introduced this, but just as a new notation, the image of F, sometimes for linear maps also called the range of F. And this is simply so denoted by imf. This is basically what's new. Not to be confused with the capital I im. This is the imaginary part of a complex number in my notation. The small im will always be the image of a map. So imf, this is by definition f of v. So very formally the space of all w in w such that there exists a v in v with f of v is equal to w. Okay, these two are special cases, namely we can get them from the previous construction. This space, which only contains 0, is a very simple linear subspace, so the easiest, the smallest simple linear subspace there is. But this is a pre-image of a linear subspace under F. F is linear, so the kernel has to be a linear subspace. And in the same way, V is a subspace of a linear subspace of itself, trivially. So the image of this is also a linear subspace. So let me formulate this as a corollary, but without proof, since this is now what I just said. This is quite obvious. Corollary 7.8. So VW vector spaces over K over K and F be a linear map from V to W. Then the kernel of F is a linear subspace of V and the image of F is a linear subspace of W. Okay, so this is now a very simple observation, and since we will make a lot of use of kernels and images in what follows, I also want to give a lot of examples at this point. So let me just insert some examples, because this is also kind of helping the intuition here, as need I guess so. So example 7.9, let us start again with a boring or with a stupid one, so to say. So again, yeah, if V and W, okay, maybe I can, just for completeness, V and W vector spaces over K. Then if we take again the 0 map, Z going from V to W, Z of V is equal to 0 for all V in V. Okay, now what's the kernel? The kernel of Z, so is everything which is mapped to 0, so everything. The kernel of Z is simply V. What's the image of, not F, image of Z? So everything what vectors are mapped onto by Z, and the answer is not much. The only thing we can get is 0, so the image of this is simply 0. Yeah, that's easy to see. First example, now second example, the other stupid example. So again, so V be a vector space over K, and consider the identity map. We've seen the identity map is the map which maps everything onto itself. So what's the kernel of the identity map? So if everything's mapped onto itself, everything that's mapped to 0 is 0. So here the kernel is simply consisting of 0. So the set which contains 0 and nothing else. This is a linear subspace, okay. Now the image. If everything is mapped onto itself, in the image we have everything, because everything is mapped onto itself. So the image of the identity is just V. Now this is the identity now from V to V, so don't be confused with the W's here. So the image of the identity is everything. Okay, so these are now the extreme cases, basically because everything is either the whole space or just 0, and now we shall see some examples where we have some more interesting kernels and images, or some less obvious. Okay, let's start with something linear. With something linear in a simple space. Let V be a vector in R3. So let's look at something geometrical. Let's take a vector in R3 which is non-zero, and we take F from R to R3. F of t is simply t times the vector. Strictly speaking, we haven't seen that this is linear, but since this proof is very, very simple, I will not do this. Is a linear map between real vector spaces. R is, as a field, a vector space over itself. R3 is a real vector space, as we've seen. So this is really a linear map. This is what I will not check here. So what are kernel and image? So the kernel of F. So we see that t times v. So what is mapped by F onto 0? So t times v must be 0. And since v is non-zero, the only possibility is that t itself is 0. So the only thing that's in the kernel is 0 again. So here again the kernel is just as small as it gets. But now let's take a look at the image. What is the image? So the image of F, this is by definition just the set of all t times v in R3, where t is in R. And to see that this is really a linear subspace, we can rewrite this as a construction we already know. This is the span. This is the span of the set which just contains the vector v. All linear combinations of v, which means all scalar multiples of v. So this is really the span of this one vector. And so geometrically, this is Mf is the line in R3 which goes through the origin and through the point v. So this v as a point in R3 with the coordinates here through 0 and v. This is the image here, and this is a linear subspace. Now let's stay in R3 and take a look at the following map. We take P from R3 to R3. Again, R3 as a real vector space, which does the following. P of x, y, z is simply x naught naught. Okay, so we ignore the y and the z and put it all onto 0. So geometrically, let me just do a very simple picture. Like if this is the x direction, this is y, this is z. This would mean that if we have some arbitrary points, let's, I don't know, say somewhere over here, this is mapped, okay, this is now unclear what this means. Let's do it like this. Okay, so we are somewhere below the xy plane, so below that. But everything what we do, this is x, y, z, the point, and we just put the y and the z coordinate equal to 0, which means that so this coordinate is equal to 0 and this one, so we just take the point which is closest to us but lies on these axes. And the same way we would have a point which lies basically in the same height, but different yz coordinates would be mapped on this. So basically the whole plane which is kind of parallel to the blackboard at this point, which goes through this point here, everything would be mapped onto this point. So we collapse the whole plane onto one point. Now, if we have this, now we can again write down the kernel and image very easily. This, first of all, this is a linear map. This is what I won't prove again this time. So what's the kernel? The kernel of P, so everything that's mapped onto 0, and we see it doesn't matter what is in y or z, the only thing that we need is that x here is equal to 0, so all points whose x coordinate is 0. So the points 0, y, z in R3, where y, z is an arbitrary point in R2. And so geometrically, if you think about this, this is the yz plane in R3. So just in the sense of analytic geometry, so the plane which is here going through 0 and now parallel here to the blackboard. Okay, this is the yz plane, and what's the image? The image of P, so, well, not that much. The only thing we can get is all points of the form x, 0, 0, and of course x can be an arbitrary number in R, so this is x, 0, 0 in R3, where x in R. And this is geometrically easy to see. This is the x-axis in R3. So this line here, so this axis here in the coordinate system, right? I've already told you that all planes are collapsed onto this point on the axis, and so of course the axis is then, the image is the axis here. So this would be a one-dimensional linear subspace of R3, this would be a two-dimensional linear subspace of R3, as you can easily show. And so there we see that we have kind of non-trivial kernel and non-trivial images, in the sense that neither of them is trivial or the whole space. Okay, now, okay, let's stay in R3 one more time, just to give you another intuitive example, because I think this is quite instructive. Let's take three real numbers, A1, A2, A3, such that one of them, or at least one of them, is non-zero for some I in 1, 2, 3. So fancy way of writing that not all of them are 0. And then we take the following way, the following map. We go from R3 to R, f of x, y, z is a1x plus a2y plus a3z. Now, the image of this is quite boring, because the image is again everything. This is easy to see. I will not discuss this in detail, but the interesting stuff would be the kernel. So the kernel of f, this is just, if we write this down, x, y, z, such that, so again, sorry, I haven't mentioned this, this map is linear, which I, again, won't prove here. The kernel of this is all points in R3 such that a1x plus a2y plus a3z is equal to 0. And this now should connect to your high school geometry. Because in high school, now if I would have an audience, I would ask what kind of object is described by such an equation. This equation here describes a plane. This is just some fundamental equation, because one of them is non-zero. This will indeed be a plane. A plane in R3 which goes through the origin. So geometrically, the kernel of f is a plane in R3 which contains the origin, containing 0. Okay, so this is kind of how you can write planes as kernels of linear maps, and it turns out basically because every plane can be described as such a thing. This is what we won't discuss in detail in this lecture, because I unfortunately don't have enough time to do more geometry. But since all planes can be obtained in this way, all planes can be described as kernels of linear maps here. So this is where geometry kicks in usually. Okay, now let's get back to a more complicated example. Let's do the example I had before, namely let I be an open interval, and we take now the space of differentiable functions from I to R, from the space, continuously differentiable functions from I to R to the continuous functions from I to R. Again, d of f is f prime, what I had before. Okay, we've seen this is linear, or we've discussed that this is linear. Now what are the kernel and image of this map? And I claim that both of them can be formulated in terms of theorems that we learned about single variable calculus in mathematics 1. Namely, what's the kernel? So the kernel of this would be the space of all functions with d of f equal to 0, which means f prime equal to 0. Okay, which are the functions, so if I had an audience, which are the functions of which f prime is equal to 0? So constantly as a function equal to 0. There we've seen that the only functions which have this property, or the functions which have this property, are precisely the constant functions. This was corollary 425a in my lecture notes from previous semester. The kernel of D is the set of constant functions from I to R. Okay, now I'm missing the space for the image. Do I have some? I don't want to erase because let me squeeze this below here and mess up my blackboard scheme. I'm sorry about that. Now what about the image? So what's the image? Which functions are in the image of this? And now we have to rethink what this means. This means a function is in the image if we can find another function such that the original function is the derivative, which means the function has an antiderivative. This is what we called this last semester, and this is precisely what this says. It's in the image if it has an antiderivative. So we have the space of continuous functions on the interval from the interval to R, and if I would have an audience now, I would ask again, which continuous functions have an antiderivative? The answer is all continuous functions have an antiderivative. And now I would ask my audience which theorem we need to apply here. Yes, Debbie? Exactly, the fundamental theorem of calculus. By the fundamental theorem of calculus, every continuous function has an antiderivative, which means that the image of D is everything. This is simply the fundamental theorem of calculus. One of the most beautiful theorems ever. Okay, so this shows the claim for this, and let me do one more example after erasing, and then let's get back to a bit more theory. As a final example, we consider a linear map on a more complicated vector space that we've already seen, namely the space R to the N, so natural numbers, the set of all maps from the natural numbers to R, which is the same as to say all real sequences. A sequence is nothing but a map from N to something, so a real sequence is nothing but an element of this. This we've seen that this is a vector space over the real numbers. Now the map we are going to study is the following. I call it S, going from R to the N to R to the N. And if we have a real sequence, I now write this as a sequence. Of course, it's a map, a sequence is equivalent. The image of the sequence xn, where n in n, is simply the subsequence xn plus 1, n in n. So if you would write these as infinite tuples, it's maybe a bit more understandable what we do. So we take a sequence x1, x2, x3, and so on. And what we do is to take this one. And the only thing that we do here is, of course, we start one index later. So we kind of drop the first element of the sequence and start with x2, which means here we have the sequence which goes like x2, x3, x4, and so on. Okay, such a map is also called a shift operator. This is why I used the letter S. We will probably learn more about them in later lectures, but it's just an example for now. And first of all, one checks that this is linear. This is also what I leave to you as an exercise. So this is again easy to see. It's a standard computation with the properties of linear maps. So what are kernel and image of these maps? So this is easy to see, actually, if you think about what's going on there. Namely, what is the kernel? The kernel of S. So we drop the first element. So if something is mapped to 0, the 0 element of the space of real sequences would be the sequence which is 0, 0, 0, 0, 0, and so on. So everything that is mapped onto 0, so all elements of a kernel, are those for which the first element can be anything, but x2, x3, x4, and so on, they all have to be 0. So the only sequences we get, or this is precisely the set, which has some number in the first component, and then only 0, 0, 0, and so on, as a real sequence where x is in R. Okay, now what's the image of this map? The image of S, let's think about it for a moment. If we have an arbitrary sequence, we can always write this in the image, because so the image of S is everything, R to the n, since all we need, so in order for the result to be any arbitrary sequence that we've given, so something holds for arbitrary sequences, in R to the n. Okay, what sequence can we choose to get this as a result of our shift? Well, the first component can just be anything. So let's, for example, take the sequence 0, x1, x2, x3, and so on. This, as applied to this sequence, gives this. So for every sequence, we can find something as a pre-image. So the image is everything. Okay, this is another example of some maybe not that simple linear map as we saw before. Okay, so the kernel and image, and we've now seen plenty of examples, and now we shall see kind of the significance of kernel and image, because they are really important linear subspaces, and we can read off some properties by them, because the next theorem summarizes kind of the first instance of such properties. 710. So again, we have two vector spaces, V and W over K. And we have a linear map from V to W. Okay, first of all, so what I want to summarize here is three properties about injectivity and surjectivity of F. Namely, the first thing is F is surjective. So again, note that this is a linear map, but the first thing would hold for everything. It's surjective if and only if the image is W. This is trivial. This is basically just writing down what surjectivity means. But I just wanted to include this just for completeness. Now comes a more interesting statement. F is injective if and only if its kernel is trivial. So this means 0 is the only element which is mapped to 0 under F. In some sense, this means that F is kind of injective at 0, so to say. So there are no two elements which are mapped onto 0. And this already implies, together with linearity, that no two elements are mapped to the same point in W under F. So it suffices to check the injectivity at one point, and so we get everything. This is the kind of the beautiful property here, which is obviously not at all true for nonlinear maps in general. Okay, and let's just summarize these. I just want to have this there for completeness, so that I've got it on blackboard once. It's bijective if and only if these two hold. So if and only if the kernel is 0 and the image of F is everything, W. Okay, so let's prove this. Okay, part A, there's nothing to prove. This is really straight from the definition. So A is obvious. The interesting part is now B. So here one direction is very simple, namely this one. If it's injective, then so if is injective, then there is at most one vector which goes to 0. This is just what injectivity means. At most one vector, let's call it V0, with f of V0 is equal to 0. So this is injectivity. But we've already seen, that was part of the remark from above, that was by remark 7.2.1, f of 0 is always 0 for a linear map. So we know this one, v0, which is unique, if it exists, has to be 0. So v0 is equal to 0. And this, of course, means that the kernel of f consists just of 0. Now for the interesting direction. Okay, we only know that it's kind of injective at 0, so the kernel is trivial, and we want to derive that it's then injective. So we need to show that any two, we do this in the following way, that v1 and v2 be two vectors in V and assume they are mapped onto the same point. Okay, but now, so by injectivity we need to show that v1 must be equal to v2. This would mean that it's injective. Now, since f is linear, we can just use this equation and play around. So this equation becomes, if I just subtract f of v2 on both sides, the difference is 0, and now the linearity means that, first of all, I can put the minus sign inside the parentheses here, and then we have an addition, and f is compatible with the additions. So this means f of v1 minus v2 is equal to 0, but by assumption, so this means, of course, v1 minus v2 lies in the kernel of f. And so by assumption, so the assumption is just the kernel is trivial. So here's our assumption going in, v1 minus v2 is 0, and thus v1 is equal to v2. So we've seen that if two points are mapped onto the same point, they have to coincide, and this means that f is injective. So this shows f is injective, which completes the proof of B. And now for part C, there's nothing to prove. This is just A and B combined. Since the map is bijective, if it's, but just by definition, if it's injective and surjective, and so we have, we just need to combine these two properties, these two assertions. Okay, this completes the proof. So we can discuss injectivity, surjectivity, and so on in terms of kernel and image. This is what we will do plenty of times. Now, we've talked about bijective linear maps, and I want to focus on them for a bit, because bijective linear maps are particularly important. It's kind of bijective maps show that kind of, between two sets that we have kind of the same number of elements, and if it's a bijective linear map, we see that it also preserves the vector space structure. And so maps for which we have a bijective linear map between them as vector spaces, we want to consider them somehow as equivalent, because they kind of behave in the very same way. And this is what we want to introduce as a, we want to introduce some terminology for this. First of all, it's just some new term. So new definition, again, we have two vector spaces over K and a linear map, or linear map will follow. We have two vector spaces over K. Linear bijective map from V to W, so bijective linear map. This is what we call, is called an isomorphism. A linear map is also called homomorphism. A bijective linear map is an isomorphism. I think we have some people in the audience with Greek roots. I think this is coming somewhere from the Greek language, but from probably the Greek language from 2,000 years ago. I don't know precisely about the roots of these words, but in some sense, so these are connected. Isomorphism is a special kind of homomorphism in this sense. So this is an isomorphism, and now I said that it's a special thing if two vector spaces have such isomorphism between them, if this exists. And this is why we also will give it a name, and we will later on see examples for why this is important. We call V and W isomorphic if there exists an isomorphism between them. So if there exists an isomorphism from V to W, And there's a particular notation for this. If the two are isomorphic, just as shorthand notation, we write the following: V, and then we have an equality sign with a tilde on top. This means V is isomorphic to W. This is what we will use later on. Okay, this is just notation. Now, first of all, a basic property of an isomorphism, which is not that exciting but important. Namely, if V and W are vector spaces over K, if F is an isomorphism from V to W, then the inverse map from W to V is an isomorphism as well. Okay, now if I had an audience, someone might maybe raise his hand and ask, well, come on, this is obvious. If the map is bijective and linear, I mean the inverse is bijective as well. So what? So what's there to show? And then I would answer, yes, the inverse is bijective. That's clear because, yeah, inverses of bijective maps are bijective. But it's not at all clear and not obvious that this map is linear. So that this again respects these vector space structures. I mean, in the one direction, yes, but in the other direction, we don't know. So this is what we need to establish, and this is what I need to prove after erasing the blackboard. Okay, let's first keep down what I just said. Since F is bijective, first of all, it has an inverse map. So F to the minus 1 as simply as a map from W to V is well defined. And again, bijective. Okay, so we want to show now that F to the minus 1 is a linear map. So, first this sum property, we take two elements W1, W2 out of W. So what we know, since we have F bijective, is there exist unique vectors. So this is, I don't know if this notation is common for everyone who was in here last semester. So there exists a unique, or no, I think, did I use this last semester? I'm not sure. This means there exists a unique, so if, existence symbol with an exclamation mark. This means there exist unique elements V1, V2 in V with F of V1 equals W1 and F of V2 equals W2. So, let's compute the following. We need to show that F inverse of W1 plus W2 equals F inverse of W1 plus F inverse of W2. So let's see, what do we have here? Here we have, we can write them as images of F. So this is the same as F to the minus 1 of F of V1 plus F of V2. Now F is a linear map. This is what we know. So this is the same as F to the minus 1 of F V1 plus V2. Okay, so here we're using the linearity of F. Now we see F inverse of F, these two cancel each other out. So this is kind of going back and forth, so these two don't matter. So the result, what we get there, is simply V1 plus V2, but since they are unique with this property, they can be described as F to the minus 1 of W1, this is V1, and F to the minus 1 of W2. And this is what we wanted to show. Okay, now we can use the other property with respect to scalar multiplications. So for all lambda in K, we further compute the following. Let us recycle this vector W1, that makes it a bit easier. So if we take F to the minus 1 of lambda of W1, so we need to show that we can pull this lambda outside. This is the same, again using the same trick, as F inverse of lambda times F of V1. And now again linearity of F, so we can pull this lambda inside. F is linear. This is F to the minus 1 of F of lambda v1. Okay, this is, and now again, f and f inverse cancel each other out, so this is the same as lambda v1, and v1, as before, is the same as f to the minus 1 of w1. And this is what we wanted to show. So this shows that f to the minus 1 is linear, and since we know it's bijective, it is an isomorphism. Which finishes the proof. Okay, so we've just traced everything back to the linearity of f itself and used some playing around inside the argument of f to the minus 1. Okay, so much for that. Now these isomorphisms, they play a special role and they have a nice consequence, and this is what I want to state already. We will probably need this more later on, but already, since we have this right now, I call this a combination of corollary and definition. Since I want to define something that's basically, the well-definedness of this thing will follow from what we've seen before. So a mixture of corollary and definition. So let V be a vector space over the field K. And we consider the following. We take GL of V. So this is the definition part, basically so introducing this new notation, and I'm giving it a name in a moment. GL of V is just the set of all isomorphisms from V to V. Okay, now the statement that is part of this corollary, then GL of V together with the composition of maps. So this is the composition, little circle in the middle. This together with the composition is a group. This is always a group, and this is called, and this is part of the definition part here again, the so-called general linear group of the vector space V. General linear group. GL as in general linear. And yes, now you might ask, if there's a general linear group, is there also a special linear group? Yes, it is, but we can't introduce it yet. This is what we will see later. So this is a group. So what do we need to show? We need to show, first of all, that this is well defined. First of all, we need to show that this composition map is actually well defined on this set. Namely, if we have two elements of GL of V, so two isomorphisms from V into itself, then the composition G circle F. So this is again bijective. This is clear. So the composition of bijective maps is bijective, and we've seen the composition of a linear maps is linear. This was theorem, I don't have it here in my notes. That was theorem 7.5. Okay, so these two together mean that the circle, the combination of these two is again an element of this general linear group. So this is actually well defined. So do this on the next blackboard. So this operation which gives us a group, so I'd write this as a circle which takes two elements of GL of V, really gives us an element of GL of V, otherwise we wouldn't need to talk about the group structure. So this is well defined. Okay, and we know, and this is kind of easy to see, obviously the composition of maps is associative. This is the property that we need for a group operation. Associative, I can't write anymore. This is associative, so the order of putting these compositions doesn't matter. This is easy to, this is just the composition of maps as it defined. And now the other two ingredients that we need for a group is inverse elements, and we need a neutral element with respect to this operation. Now, so first of all, we've seen that the inverse is of, so if F is an isomorphism, then the inverse is an isomorphism. This is what we've just seen. So this is again in GL of V. So it's kind of obvious which we take as inverse elements with respect to the composition. Since the composition of F and F minus 1 is the same as the other composition, F minus 1 composed with F, and both of them just yield the identity on the vector space. So this shows basically that these two come together to this identity, so this should be our neutral element. So the identity is what we need as a neutral element, and this is also what happens. So the identity obviously has the properties of the neutral element, since if we have an arbitrary isomorphism and compose it, or an arbitrary map actually, and compose it with the identity here on V, this is of course simply F, because the identity doesn't change anything. And the same as we take the other composition, F composed with the identity, this way around. If we do this before, nothing changes at all. So these two, this shows basically that the identities on neutral element, these are the inverse elements. This is the inverse element of F. So we have the existence of a neutral element, yeah, F to the minus 1 is, no, let's start with the identity. Identity of V is a neutral element of GL of V with a composition, and F to the minus 1 is the inverse element of F in this group. So really, I mean, it's an inverse map, but so far it's the inverse element abstractly of this group operation in the group GLV, yeah, with the composition. And since this shows, so we have a surjectivity, we have a neutral element, we have inverses, so this shows that GL of V is indeed a group. So we have interesting algebraic structures on these maps. So we really have a group just consisting of these isomorphisms of a vector space. This is what we need and study in bigger detail later on. But so far we just have this construction here, since this was kind of, yeah, now easy to get. Now the last thing in this section, and the last thing so far about isomorphisms, is that I want to show they have a nice property, namely actually you can take an arbitrary linear map, take a nice restriction of this map and get an isomorphism. By this I mean the following. So now I need again two vector spaces over K, V and W, and a linear map from V to W. Okay, so namely this might be neither injective nor surjective, but if U is a linear subspace of V, and namely it is a complement of the kernel, so of the kernel of F, then the following restriction, F restricted to U, so we just consider F on U, and consider this codomain, not the whole space W, but just the image of F. So we restrict the domain to U and the codomain to the image, which might not be everything. Then this map is always an isomorphism. Now, how to see this? Okay, so we know it's linear, so restriction is again linear, that's trivial. So we only need to show it's injective and it's surjective. So how do we get that? First of all, if we have an element in the image, let W be an element of the image of F, then we need to see that it's an image of this map. So far we only know there exists an element in V which maps onto W, but we don't know if there's an element in U, which is smaller, which maps onto this element as well. So how do we see this? So that W in the image and V in V be an element in the pre-image, so with F of V equal to W. So, what do we know? This is only an F, but we know since this is a complement of the kernel, this means V is the direct sum of U and the kernel of F. This is the definition of a complement. There again exist unique vectors, and this was a theorem. Do we have a theorem? Yeah, theorem 638. By theorem 638, there are unique vectors V1 in U and V2 in the kernel of F, with V is equal to U1 plus U2. Then it follows that if we take this element here of U, so here we have the restriction well defined on U, so we take the restriction F restricted to U. Looks a bit weird, but this is what I'm doing here at this point. So this map applied to V1, by definition of the restriction, this is the same as F of V1. Now, this here is in the kernel of F, which means if I add F of V2, I'm just adding 0, so this is the same as here. So here I really only need that V2 is in the kernel of F. Okay, now F is a linear map. So this is the same as F of V1 plus V2, and here I called them U. Sorry about that. This was of course V1 and V2. Sorry if this was any confusion. So here I've chosen them just precisely so they add up to V, and V is just by definition chosen that this equals W. So we found an element of U, which is V1, such that which is mapped to W under this restriction, and so W is in the image of the restriction. And this shows that the image of F is a subset of the image of the restriction of F to U. The other inclusion is obvious, since this is just a smaller space, so, and this is just a part of F, so this would be only a part of the image theoretically. So yeah, now I'm losing space. Do I have anything left to squeeze? No, I don't. Then let me quickly erase. Okay, so we've seen that the image of F lies in the image of the restriction, and since U is a subset of V, this obviously means that the image of the restriction is contained in the image of F. Yeah, so we really get that the image of the restriction is the image of F, and this means that F restricted to U is surjective, since by definition our codomain is just the image of F. Actually, this inclusion would have been enough already, but anyway. So this is a surjective map now for the injectivity. So if U is in, oh that's nice, it's called V, let V be in the kernel of the restriction. So if F lies in the kernel of the restriction, since the kernel is just, the restriction is just F itself, then also V must lie in the kernel of F, obviously. But this is defined only on the space U, so V is an element of U. But this means V lies in U intersected with the kernel of F, but since U is a complement of the kernel, this intersection just contains 0. So V is equal to 0, hence the kernel of F restricted to U just consists of 0. And by the previous theorem, whose number I forgot, I have to look on my sheet, Theorem 710, B, Theorem 710B, this implies that F restricted to U is injective. So we've seen F restricted to U is an isomorphism, which we wanted to show. Okay, this concludes the proof of this chapter. Sorry, of this. This concludes this section. That's what I wanted to say. So this was general properties of linear maps. As I've said before, in this lecture we want to focus on finite dimensional vector spaces and then maps between finite dimensional vector spaces. We've seen in chapter 6, so in the end of Mathematics 1, that the finite dimensional vector spaces, we have used always the terminology of bases, of generating sets, so vector spaces with finite generating sets were finite dimensional, and we have seen properties of them. So in order to study finite dimensional vector spaces in detail, we first have to kind of take a look at the interaction of linear maps and generating sets, and then basis and dimension, of course. But this is what we first have to investigate. So what do linear maps do with bases, with generating sets? What happens? And this is what we're going to do in the next section. So I hope to see you all back in the next video.